equation will turn into 3u squared minus 7u minus 6 equals 0. Do we all agree with that?
Yes. Which factors to 3u
Plus 2u minus 3 equals 0. And then you can get two solutions from this.
Yes. I got u equals negative 2/3.
Negative 2/3.
And u equals 3.
U is 3. We still all on board here with this? This making sense? Okay, and now it's just a matter of trying to figure out what x is.
Then I substituted back in the u.
Okay, so let me do that for you now. So this u is x to the negative 1
That's correct.
equals negative 2/3. And then this one is x to the negative 1 equals 3.
I don't know if I did was right, but what I did was I timed each side by x to the negative 1 power to cancel out the 1, or no?
You multiplied by x to the negative 1? Close. Anyone else try something? Yes.
I know that x to the negative 1 is 1 over x.
Okay, x to the negative 1 is 1 over x. You could do that also.
And then I multiplied negative 2/3 by x. It was really long.
Okay, so both those ways are going to work.
Okay, so
Okay.
what I did was right.
Yes.
Okay.
If you, now, there's different ways of doing this. Let's see. Let's try this 1 over x way, just to see if we can see what would happen here. So at that point, what did you do here?
Multiply by x.
You multiplied x on both sides. So if you multiply the left side by x, and you multiply the right side by x, then you just get a 1 here, and then negative 2/3 x, and that's a linear equation, right? And to get x by itself, you could just multiply both sides by what? The reciprocal of this, right? Negative 3/2. Multiply this side by negative 3/2. You get this. Multiply negative 2/3 times negative 3/2. That's 1, right? So that's just going to give you 1 in front of x. So x. That's one way to do it. Here's the way I would do it. Okay, this is just the way I would do it. X to the negative 1, I'm going to raise this side to the negative 1, and I'm going to raise this side to the negative 1. Now, the reason I did that is because what happens when you take something to a power? You multiply the powers. What's negative 1 times negative 1? Positive 1. So that's just x to the first power, isn't it? And the right side is 3 to the negative 1, which is the same as, close, 1/3. 3 to the negative 1, what's that?
He's accidentally hitting the tripod.
I still see me in there. It's all right. Yeah, we're good. So we get 1/3. See that? Now I could have done that over here too. If I did this to the negative 1, this to the negative 1, this side becomes x. What's a fraction raised to the 1/3? Flip it. That's all that happens. So I'm using a property of exponent that says if you have x over y to the negative 1, it's y over x to the positive 1, which is just y over x. Either way, you're going to get the same result. Yes?
Question. In the beginning of the equation,
Mm-hmm.
could we have the way you're multiplying those out to cancel out the negatives? Could we have done that in the beginning?
What did you multiply by?
Well, like if 3x, the negative second power,
Uh-huh.
could you like times negative 1 to make it 3x squared?
Like raise it to the negative 1? You could not. And the reason why is because you would have to raise this entire side to the negative 1 and then the entire other side to the negative 1. You couldn't do each one individually to the negative 1. What you could do is this, though. This would be another path leading to the same answer. It was minus 7x to the negative 1 minus 6 equals 0. Just so you know, I might get a phone call that I might have to take outside. I just got like an emergency phone call. So if I get another one, I'm going to take the call. One thing you could have done here is recognize that this is this. And then you could have said, all right, I'm going to clear fractions and multiply everything by x squared. See, what happens if you multiply this by x squared?
Then you get,
The x squareds go away,
yeah.
and you just get 3, don't you? Minus, what happens if you multiply this by x squared? Here, I should do it. I'm multiplying this by x squared, x squared, x squared, x squared. Everything. So the x squareds cancel, get 3. Over here, one of the x's still stays, right?
Right. So 7x
Here,
minus 6x squared equals 0.
that's a quadratic equation. Move everything to the other side to make it, I'm going to move everything to the right side to make this a positive.
And how did you get,
Zero should be on this side.
just backing up a little bit, how did you get
Hold
x
on.
squared?
Where?
Like, for what you should multiply everything by?
I looked at the, for an LCD, least common denominator, I have x squared here, I have x here, so x squared should account for it. Now, what was the other question?
Would the quadratic equation actually be negative 6x squared minus 7x plus 3?
Yes, it would be. It would be negative 6x squared minus 7x plus 3 equals 0.
But then you just move it over to the other side.
But yeah, with the equality, I can basically move this over here, make it positive. This over here, make it positive. This over here, make it negative. The left side would be 0 now. So I just changed all the signs. You're always free to do that with an equation. And then here, I could try and see if I could factor this. And my guess is going to be something like 3x, 2, I don't know. Is that right? 1, 3, is that? No, hold on. Oh, well, it might be, what were my two answers? It was negative 3 halves and 1/3. So, something ain't right here. No, 3, hold on, there, and then here, 3. Is that it? So 6x squared minus 9, plus here, minus here. Okay, so 6x squared plus 9x minus 2x minus 3, that would work. So I'm just showing you a different way of doing it. This way does not use the U substitution, right? It just clears fractions. That's all that does.
Like you said, there's different ways about going.
That's right.
Yeah, that's right, as long as your bricks don't fall.
Yeah. Okay, I'm not going to work through this one. I just want to show you, and then you can tell me what I should do. How about 3x to the 4/3 plus 5x to the 2/3 minus 2 equals 0. So does that look like quadratic form to you?
It's not as it is.
Could you substitute x to the 2/3 for u?
U is x to the 2/3. That should work as long as this is that squared.
Yeah.
Is it? It is, right? So that should work for that problem. And then you work through. I'm not going to work through it, but that would be the proper substitution for that. How about something like this? X squared minus 3x minus square root of x squared minus 3x equals 2. So if you look at that initially, you might be thinking radical equation, right?
Yes.
And you could probably get this problem by doing the steps for a radical equation. The first step would be what? Isolate the radical. So you would get this radical by itself. I'd probably move it to the right to make it a positive, and then I'd move the 2 to the left. Now don't write this down, but this is where you'd be. That's where you'd be, right? Now if you square this side, that's great, right? But if you square this side, you're squaring a trinomial, which means 3 terms times 3 terms, right? That's going to be a mess. It's better if you're able to recognize that this right here is x squared minus 3x to the first power, and then minus x squared minus 3x to what power? Half. The square root is the same as the half power. This 2 right here, let's move it over. Minus 2 equals 0. Y'all still with me on that?
Yeah.
Do y'all see it? What's that? So far? So u is, on this one, u is x squared minus 3x, the whole thing, to the 1/2. Right? Do you see that? This is u. What happens if I square this? It's just this, isn't it? So this actually turns into, if I were to keep going with this problem, my next line would be what?
U squared.
U squared, right? Because that's u squared. Minus u minus 2 equals 0. You see it? And then this becomes u, what, minus 2u plus 1 equals 0? Looks like I'm taking this the whole way. What are my 2 answers here? 2 and negative 1. But what was u? This right here, right? So you ready to substitute that back in? So I have this right here, right? X squared minus 3x to the 1/2 equals 2, right? And the other one is, this equals what? Negative 1. So I have another one that I have to solve. You all okay with that? How would you solve this?
Put it back into the square.
You want to go back to the square root and then square it? Yes. Or you could just square it now. It's up to you. Right? Like this is a square root, isn't it?
Yes.
This is a square root. And now both of these are radical equations, aren't they? So you could square both sides and then continue. This is a pretty interesting problem, huh? So what if I square, let me just do the top one. I'm not going to do the bottom one. If I square both sides here, I get x squared minus 3x equals 4. Got to square both sides, right? So I square both sides there. What type of equation is that?
No, that's quadratic.
That's quadratic. Four negative 1. Potentially. Why do I have to check my answers?
Because you squared.
I squared both sides, right? I squared both sides.
So then you'd have 4 potential answers. In the
Yeah, it looks like I'm going to have 4 because I'm going to do this one also. Ooh, that one's going to be ugly. That's going to be ugly. Because when I do that one and I square both sides, I'm going to get x squared minus 3x equals 1, right? I'm going to move the 1 to the other side, and I'm not going to be able to factor that, am I? So I'm going to have to use quadratic formula on that. That was in the book, so I decided I would put it up there. All right.
That one semi-randomly?
Well, randomly, I just looked at, here's number 65. All right, that's a good mixture. Here's a problem that is just weird, because you haven't seen this before. And it's hard for you to understand why you'd want to do this right now, like what's the point of this? But again, this has a lot to do with what's coming later in future classes. Let me write this up here and then let me see what you think. If k equals x plus 3 over x minus 4 and k squared minus 3k equals 28, find x. If k is equal to x plus 3 over x minus 4, and k squared minus 3k equals 28, then find what x is.
So use the second of those two to solve for k.
Okay, so for this one, it's a quadratic equation, right? You can solve it for k. So you should be able to solve this and get two numbers. And then you can just replace that, right, k. You're going to get two k's here. Replace that k with one answer and then solve for x. Then go replace k with the other answer and solve for x. You should get some solutions, yeah? So let's try it. Let's go ahead and solve this one for k. Okay? Okay. It's factors k minus something, k plus something, I hope. 7 and 4. -7, +4. So k is either 7 or k is equal to -4. So now we come up here and we know a relationship between k and x, don't we? So let's first start with k is 7. If k is 7, this becomes 7 equals x plus 3 over x minus 4. And then I multiply, what, clear fractions here? I can clear the fractions, multiply both sides by what? X minus 4. Multiply both sides by x minus 4. This is called a rational equation, right? It's an equation that's a rational expression in x. So if I multiply the left side by x minus 4, I'm going to have to do that. If I multiply the right side by x minus 4, I get what? I just get x plus 3, right? Because they go away, which is why I did it, right? What type of equation is that? Linear. It's a linear equation in x. I may as well take this all the way. 6x equals 31 and x is 31/6. That's one answer. Then I would go, remember I had another k? The other k was what, -4? So you put -4 here, you do the same thing, and you get another x value. The other x value should turn out to be 13/5. Okay. So that's all we have for today. I think I've covered mostly everything that should get you through the homework. Just make sure there's no loose ends here. I didn't do any factoring or any solving equations where you had to do grouping. Y'all know what I'm talking about when I say grouping? I'll do one up here just so you can see it. So when you get to your homework, you're like, well, he never showed me anything like that. Start calling me names. Something like this. That equation is not quadratic, right? It's also not a quadratic form because we need 3 terms to be quadratic form, don't we? And so we had 4 terms. We move everything to one side, put it in descending order. And because there's 4 terms, you were supposed to factor by grouping. And so what you do is you split this up, and it kind of depends on how you learned it. Like you're supposed to split it down the middle, and then you're trying to pull a GCF out of here and a GCF out of here. So what's the GCF you can pull out of this?
X squared.
You can pull an x squared out, and you're left with 3x plus 4. Now for grouping to work, for it to work, you're going to have what sitting in parentheses there? Same thing, 3x plus 4. So I like to just put it here and see if there's a way that I can get back to these 2 numbers by putting something out here. -9, right? -9 distributed back through would give you this and this, so that should work. And then on the next line, what do I write? X squared minus 9, and then 3x plus 4, like that. And is it okay if I wrote it the other way around, like put this one in front like that?
Yeah.
Yes, that's okay? So multiplication is commutative. And then this is difference of squares, x plus 3x minus 3. 3x plus 4 equals 0. So you set each of these equal to 0, and you should get 3 answers. -3, +3, -4/3. So that's the grouping. You all remember grouping? Okay.
Instead of writing out like x equals 3x minus 3, could you put x equals plus or minus 3?
Yes, you could do plus or minus 3. Okay, I have 10 minutes, and you can start packing up if you'd like, but I'd like to show you something. Because you paying to be here, right? So I may as well give you your money's worth. Or somebody's paying. There's a story that goes with this, all right? There was a mathematician. His last name is Gauss. I think his first name was Frederick, but I always forget. And the story goes like this, that this kid, when he was in first grade, this is back in the late 1800s, I believe, when he was in first grade, the teacher had gone in that day with all the little first graders and asked them, what's 1 plus 2 plus 3? And of course, all the little first graders were like, 6, right? Okay. So the teacher said, all right, today, class, since you understand how to do that, I'd like for you to add up all the numbers to 100. Now, this is the late 1800s, so there were different standards back then. So this isn't like completely out of the realm of, like this. They were doing arithmetic at an earlier age. So this isn't completely crazy to ask them to add up the first 100 numbers. But the idea was that the teacher wanted to keep the students busy and didn't really want to have to deal with them that day. So as the story goes, Gauss was messing around, and they used to write on little, they had like little chalkboards instead of paper. They had little slate tablets, and that's what they would write on. And so he was doing some writing, and within a few minutes, he turned over his little slate, and then he crossed his arms, and he just sat there and was quiet, which is what they used to do back then because they also had discipline and things like that. And so he's just sitting there, and the teacher kind of notices, that's the sign for being done, right? So he goes over to Gauss, and he turns Gauss's little slate over, and Gauss has written down this. N times n plus 1 divided by 2. And so the teacher's like, you know, what is that? And Gauss said, well, you asked me to add up the first 100 numbers. If you want me to add up the first n numbers, so n can be 100, or it can be 50, or it can be 1,000, or it can be 1,000,000, doesn't matter what it is, then this formula is the formula you would use. So let's just see what Gauss was talking about. If we wanted to add up just the first three numbers, 1 plus 2 plus 3, what would n be?
3.
N would be 3. So let's just plug 3 into this formula. 3 plus 1 over 2. This is what? 3 times 4 over 2, which is 6, right? Now that doesn't mean the formula is correct. It just means that it worked that one time, which is not good enough to say it always works, right?
But that's still incredible.
But that's a good sign, isn't it? That it worked? And if it worked for 4, because what if I did 4? Then the answer would be what? 10, right? This is 6, plus 4 is 10, right? So let's try 4 in here. 4 times 5, 20, 2, 10. It works? Okay. So the teacher, turns this over, looks at it, sees the formula, and actually the teacher didn't say, what is this? The teacher knew what this was, because this formula was what was known. Okay? So Gauss did not come up with this formula like he wasn't the first one to ever discover it. But
that's so.
the teacher was like, where did you see that? Okay? So Gauss, the story goes, and I don't know if the story is really true, but Gauss did so many absolutely incredible things in mathematics, it's not a stretch. He was a prodigy, a genius.
Gauss Jordan?
No, that's a different.
I was like, I took business Gauss, so I figured.
You're thinking of elimination,
Yeah.
where you're doing like systems of equations.
Yeah.
This is the Gauss.
Oh.
Yes. But Gauss Jordan is named, I think, for 2 different people.
Oh, okay. So
It's not the same person. It's called Gauss Jordan elimination.
Yeah.
Gaussian, we actually call it Gaussian elimination. It's how you solve systems of matrices. That's him.
Yeah.
But that's just a little piece of what he did.
Oh, okay.
Yeah. So the teacher's pissed off. This is supposed to be a day-long project. These kids weren't supposed to be bothering me. So the teacher's insistent for Gauss to tell him, who showed you that formula? Where'd you get that formula from? And Gauss was like, I just came up with the formula, like, I did. And so Gauss went to show him how he got the formula, and that's what I'm going to show you. And you're going to be blown away by just how easy it is to show this is true. All right? Here we go. So I'll explain it to you in a simple way first. Gauss said, all right, I want to find the sum, I'll call it S, of 1 plus 2 plus 3, and I'm going to go out all the way to 100, okay? So let's just write the last few down, 97, 98, 99, and 100. Well, Gauss was smart enough to realize that when you add numbers together, it doesn't matter what order you add them, right? 1 plus 2 is 2 plus 1. It's called commutative property. So Gauss said, look, I'm going to rewrite this sum, but I'm going to write it backwards. The last number would be 1, then the one before that 2, the one before that 3, the one before that 4, right? That's backwards. And then Gauss said, all right, well, look, there's something I notice here. That if I take these rows together and we add them, right? S plus S, so this sum plus this sum is 2 of the sums, isn't it?
Yes.
So he said this left side is twice the sum, but the right side is where there's a pattern. Do you see the pattern? If I just add straight down, what's 1 plus 100? 101. What's 2 plus 99? 101. What's 3 plus 98? 101. And this keeps going, right? All the way down till you get to the last one, which is 101. Now remember what multiplication is. If I say 5 plus 5 plus 5, the shorter way of saying that is 3 times 5, right? So when we have repeated addition, we use multiplication. So this is just repeated addition. This is 101 repeated how many times? 1, 2, 3, 4, 5, 6. 100 times, right? So this is just twice the sum is 100 101s. Yes? But that's twice what I want. So if I just divide this by 2, then that's the sum, isn't it? Make sense? Okay, but that isn't even the way Gauss did it, all right? That's just so you would understand. So this is how he did it. I'm going to add out to n. So what's the number right before n? Well, whatever n was, take 1 away, right? So this is n, take away 1. What's the number right before that? N take away 2. And so on and so forth. So if I write this row backwards, the last one's still 1 and 2 and 3, right? But on this end, it's what? N at the end. The one before that is n minus 1. The one before that is n minus 3. And now look at the pattern when you add down. What's n plus 1? N plus 1, right? Whatever the hell n plus 1 is. What's the next one? N minus 2 plus 2, right? That's what I'm doing? That's n plus 1 again. N minus 3 plus, sorry, this should have been 2. N minus 2 plus 3. N plus 1 again. This is going to happen the whole way down, isn't it? To the very last one. N plus 1. How many n plus 1s am I going to have? Not 100. 1, 2, 3, 4, 5, 6, n of them, right? So I'm going to have repeated addition. So there's going to be n plus 1s, right? But that's twice as much as I need. So I half it. And that's the formula he had written down. N times n plus 1 over 2. Well, the story is that he was in first grade. So this is what separates, I think, geniuses from just average people like myself and you and everyone else. Now, you can be a genius in your own right, whatever it is that you do. You may be genius at something, but I don't think there are any mathematical geniuses like this sitting in this room, inclusive. Okay? This is brilliant, right? How many of you followed this? How many of you followed what I did here? Yeah? Kind of? All right. So it's not that it's like totally out there. It's the fact that someone actually came up with that without any prompting or any guidance, just kind of developed it on their own. That's amazing to me. So I just want to show you that. That's just kind of cool. So if someone ever asks you, to add something up, the first integers, that's the formula for it. Have a great day. See you on Tuesday.
Kind of funny, just over the.
I forgot to sign pass the sign-in sheet around. Oh well, it happens.
Funny, just over the summer break, I was playing some game.
What's the sign there?
No, people are already gone. It's all right.